All right, we are back. That was awesome, Herb. Thank you so much. It's so nice to go through these talks, just one amazing talk after the other. I know yesterday might have got a little dense towards the end. Hopefully today we'll keep it a little lighter towards the end. But right now we're going to go very deep with the one and only Scott Myers. Woo!
Thank you very much. You know, after Herb's keynote, I was overcome with this feeling of love and pleasure and how wonderful the world was. And I'm not used to having that feeling, but I reviewed my notes for the slide, and I'm grounded now. So I'm feeling better. It's going to work out okay. Last year at GoingNative, one of the things Herb talked about was apparently how I'm going to be writing a book. And I thought, I should probably do that then. So I've been trying to figure out what it would mean to be effective in the revised version of the language since about 2008, 2009. I'm a little bit of a slow learner, but after 4.5 years, I feel like I have some ideas of what it would be like to take this new language and use it in ways which will help you get your job done better without falling into too many pitfalls. So I'm working on a book right now called Effective C++ 11/14, and I want to give you some information of what I expect will probably end up being in that book. The book itself, it's going to be completely new material, so it's not going to repeat anything from my other books before. And it's a little bit different, I think, from the approach that other people are taking in the sense that I'm going to assume that readers already know C++ 98 pretty well, so I'm not going to cover C++ 98 stuff. It's not an introductory book. I'm going to assume that they have some basic information about C++ 11, so I don't need to explain what is an L value, what is an R value, except for very, very briefly in the introduction. And I'm going to cover information from C++ 14 when I consider it appropriate, but I'm not going to assume any background in C++ 14 on the part of the readership. It's going to be the usual guideline-based approach that I try to do in the past, try to show people things that either you should do or you should not do in order to be able to use the language effectively. And right now it's looking like it'll be finished sometime second quarter of next year for some definition of finished. So, now, I sat in the front row yesterday, and I'm watching everybody else give their presentation. And so, because I'm also a speaker, in addition to looking at the content, I'm looking at their slides, and I'm looking at their presentation style. And it became very, very clear that I do not have enough pictures in my slides. It made me feel very bad, so I said, no problem. We have technology that we can solve this problem with. So I went to Google, and I searched for effective and images. I got to get a picture in there, right? And so this is what came up. I said, okay, that's enough images. Not quite sure what to make of that. So that made me feel better. But at the same time, you've got people and they've got like things bouncing on the screen, and they clearly are masters of the PowerPoint ninja. And that's not me, but I felt like I have to compete. So here it is. Are you ready? Let it not be said I had nothing that moved and that I didn't use enough colors. I want to talk about C++ 11, C++ 14. I want to talk about guidelines. I brought 3 of them with me. I don't know whether I'm going to have time to cover all 3 of them. The first 2 we'll cover for sure. And the first one is to understand standard move and standard forward. And I've been talking about C++ a lot to a lot of people. I've been giving various presentations. And what I have found is that many, many people have no idea what standard move and standard forward do, which is kind of important because they're used very frequently. And I'm going to start by telling you what they don't do. So what you need to know is standard move doesn't move. Standard forward doesn't forward. In fact, neither one of them do anything from a runtime perspective. They generate absolutely 0 code. So now that you know what they don't do, it's kind of relevant to figure out what they do. They are casts. All they do is talk to the type system. They don't do anything else at all. In particular, move is an unconditional cast to an R value. That's all it is. And forward is a conditional cast to an R value. All they do is talk to the compiler and essentially say to the compiler, this expression here, regardless of what you may think, is an R value if it's a move. And if it's a forward, it says, okay, this expression here might be an R value. And we'll talk about the conditions under which it actually becomes an R value. So that's moving forward. And in case you don't believe me or you'd like to have a better sense of this, what I'm showing you now is a almost standard conformant implementation of move, where I've highlighted, number one, the name of the function, because there's a fair amount of cruft at the beginning, which is just the template declaration and the return type. And notice the only executable statement is the return statement, which consists of nothing more than a static cast. So move simply takes its argument and does a cast that turns it into an R value. Now, it has been suggested that perhaps a better name for this would be something like R value cast. And that's actually not a bad idea in my view. Now, it has the name move because normally you use it to set things up to be moved. But move itself doesn't do any moving. All move is doing is casting something to be an R value. So that's move. It's interesting to note that in C++ 14, you could improve the implementation somewhat in terms of making a little bit less duplication. In particular, if we go back one slide, notice that the pesky return type, which is the type name remove reference t : type, that's the return type. It's in front of the function. And then you'll also notice that inside the implementation, we have a alias declaration. So we're saying the return type is also the same thing, type name remove reference of t : type ref. Well, you probably don't really want to type that more than once. It's kind of unpleasant anyway. So in C++ 14, you could replace that with decal type auto, which would simply look at the return statement and figure out what the return type was. And it turns out there's also a special alias in C++ 14 that eliminates some of the cruft when you're specifying what that return type is. They both do the same thing. This doesn't change the semantics in any way, just sort of a nice example of how you could take advantage of a couple of new features in C++ 14 if you were implementing something like move. Having said that, there's not a lot of things like move that need to be implemented. Nevertheless, it's worth seeing how they can be applied. So let us suppose that I have some data structure, which I've cleverly called some data structure. And inside the data structure, I have a string data member. And then I have some variable of type some data structure, SDS. So SDS is just an object that has a string inside of it. That's all it is. And now I decide I need to write a function which is going to take a string. It's going to do some processing on the string. And then when it's done with the string, it's going to add it to some data structure. Now, possibly because I'm under the influence of a fairly well-known blog article by Dave Abrahams that says, want speed, pass by value, which is sort of a provocative title because, I mean, let's face it, when you say want speed, every C++ programmer starts drooling. So, of course I want speed. And then yesterday, Sean said if you have a sync function, then what you want to do is you want to pass the argument by value. I'm easily influenced. So based on Sean's argument, based on Dave's argument, that's 2 against 1. So what I decide to do is pass by value, because process and add is going to take this thing, do some processing, and then it's going to add it to a data structure. It's a sync function. But at the same time, I'm thinking everything that I do inside this processing function is going to be a read operation. I'm not going to modify it in any way. And as a result, I think, well, that means I should really declare it const. I don't want to accidentally change it. So I'm going to, in this case, pass it by const value, which seems perfectly reasonable so far. But at the end, when I'm done with it, I don't need it anymore. And I've got to add it to this data structure. So I'd like to add it to the data structure in the most efficient way possible. And we realize that, of course, the best way to do that is to do a move on it. So what I want to say is I'm going to move S into this data structure. So far, everything seems like a pretty reasonable progression of logic. And this is reinforced by the fact that it compiles, it runs, and unless you've been writing really, really picky unit tests, it will pass all of your unit tests as well. So, success, ship this puppy, right? And it's only later that you look and you go, wait a minute. I'm applying move to a const object. And last I checked, moving things generally changes them. We reach inside, we get their data, we give it to somebody else. That usually leaves some scarring on the object that we've ripped the guts out of. And did you notice the part about compiles, runs, passes unit tests? So it'd be interesting to know exactly what's going on. Now, when we make the assignment to a string, if I go, well, actually we'll do it here. So this is that same line where I used the move. And what you'll notice is I'm doing an assignment from a string on the right and a string on the left. So this is just a string assignment. There's two string assignment operators in the string class. There's the copy assignment operator. It takes a const string ref, as usual. Then there is the move assignment operator, which takes an R value reference to a string, as usual. So the compiler has to figure out, when I pass the result of move to string to do an assignment, which of these two overloads am I going to call? Now, what I said was move takes its argument, which is S in this case, and it casts it to be an R value. So we're calling an assignment operator with an R value, but we're calling it with a const R value. Move does not change the const of the object that it's being dealt with. So now overload resolution kicks in, and the compiler says, okay, I have a const R value. And it looks at the two possible overloads. Now, it can't call the overload taking an R value reference, because that is an R value reference to non-const. And therefore, calling the move assignment operator would be a violation of const correctness. So that call is off the board. But the other one, which is an L value reference to const, that's perfectly fine. The fact that we happen to be passing in an R value is okay, because you can bind R values to L value references to const. And as a result, what you end up doing is calling the copy constructor for the string. This is why your code compiled. This is why your code ran. And this is why your code probably passed all of its units tests, because if you simply were checking the end result of the system to make sure that you actually got the string value into the data structure correctly, it's going to pass that test as well. It's interesting to note that this business of overload resolution going from something which looks like a move in the source code, as it does here, but actually ends up performing a copy, is a really important backward compatibility feature of C++ 11. This is essentially the same reason why, if you take some type out of a library that nobody has looked at since 1997, and you apply move to it, that code will compile. Now, you can't move this thing. In 1997, it didn't have move operations. It's because you cast it to an R value, and then the overloaded assignment operator or copy operator, whichever you happen to be looking at, it's not going to have a corresponding move operation, and therefore the R value, which is the result of calling move, is simply going to get bound to the copy operation, which is why requests to move objects that don't know how to be moved decay into copy operations for backward compatibility. But that same backward compatibility means that if, for example, you have a constant object which does support move, and you cast it to an R value, it will be copied. So move doesn't move. Two lessons here. The first thing is you do not want to declare objects const if you don't want to move from them. And if you think about it, this makes a lot of sense. Moving from something typically modifies it. Declaring something const does not permit it to be modified. When request to move butts heads with const, const wins. So that's the first lesson. And the second lesson is using move doesn't guarantee anything will actually be moved. So many people I see, they're reading through code and they go, oh, here's a move, this means it's going to be a move. And that's often true, but you cannot make the assumption that just because you see a use of move in the source code, that the thing you are applying it to will definitely be moved. It depends on some other factors. In particular, if that object itself is const, it's definitely not going to get moved. And if the type on which you're applying the move operation, the move cast, doesn't support moving, you're going to fall back to copy. Yeah?
Is there any diagnosis made of this? Because otherwise you look at that and say, oh, look, I'm doing a move. You think you're doing a move. The compiler says, no, you're not, but it doesn't tell you. Is there any way to find out that it is saying, no, you don't?
Okay, so we have two questions. Question number one is, will you get some kind of a compiler warning for this? number one, I strongly doubt you're going to get a compiler warning, because what that would mean would be that any pre-C++ 11 type that was ever used inside the standard library would issue more warnings than would fill this room. So very unlikely. And then the second question was, is there any way that you can be aware that this is happening? Yes, pay really close attention. And step one on the road to attention is to simply get into your head that the use of move doesn't guarantee a move will occur. It sets up a move by casting its argument into an R value. But it doesn't do the move itself. It's actually the overload resolution that's going to do the move. So that's the best I can offer you right now. Sorry. But in C++ 14, it's exactly the same. Nothing changes. So that's move. So let's move on to forward. So forward, let's suppose I've got a couple of processing functions, and I don't know what process does, but it takes widgets, and in some cases it turns out it's more efficient to be able to move from widgets than to copy them. So I followed the convention of C++ 11, which is I've overloaded on an L value reference to a widget and an R value reference to a widget. So this is a convention. This is the sort of the normal way of distinguishing L values and R values. That's fine. And then I have this function, or actually it's a template log and process. Now what log and process does is it takes a parameter of any type, L value or R value, makes a log entry, and then what it does is it calls the process function by forwarding the parameter. This is the conventional use of standard forward. There's nothing surprising here. Let's take a look at what calling code might look like, because that's what motivates what's going on inside forward. So if I have a widget object W, and now I call log and process with W. In other words, I'm calling with an object that's an L value. So if it's an L value, that means what forward's going to do is forward as an L value, and ultimately the process function will get an L value. We'll call the L value overload. This makes sense. I have an L value argument, the widget W. I pass it through log and process, and ultimately it ends up in the process function where I want it to be processed as an L value. On the other hand, if I call log and process with standard move of W, we now recognize that the only thing move does is take W and cast it to be an R value. That's all it does. So now I'm passing an R value widget into log and process, where ultimately it's going to get forwarded to the process function. Now, inside log and process, there is a parameter. The name is param. By virtue of being a named object, you can take its address. By definition, that makes it an L value. So the parameter param inside log and process is absolutely an L value. So if we pass that to process naively, the process overload is going to see an L value, and it will always call the L value overload. But if we go back down to the bottom line, the calling code, on the very last line there, I'm actually passing an R value. So what I need to do is find a way to take the R value, which was passed into log and process, where it becomes an L value, because now it's the parameter called param. I have to convert it back to an R value so that the appropriate overload of process will be called. That's what standard forward does. Standard forward says, if the argument that was originally passed in was an R value, then turn param back into an R value, even though it's an L value inside this function. And if what was passed in originally to log and process was an L value, then the fact that param is an L value should go unchanged. That's why it's a conditional cast. It casts it from the L value that param is into an R value if and only if the argument that was passed into the function originally was an R value. So as I said, param is an L value, and therefore forward casts param only if an R value is passed in. It is therefore a conditional cast. It turns out that whether what was passed in was an L value or an R value is encoded in the type parameter that is deduced when we call what we call forward. No, actually, it's the login process. Sorry. Login process, the type T will encode whether it got an L value or it got an R value. So what that means is conceptually, we can think of implementing forward as is shown here. Now, bearing in mind this audience, which includes people who write compilers and who write standard libraries for a living, I want to apologize from the bottom of my heart that as you look at this code right now, you are in tremendous pain and torment. But remember, this is a conceptual implementation. This is just trying to get the idea across. So what forward conceptually does is, first it says is, okay, the type T, if it's an L value reference, which is the magic way that it says that what was originally passed in was an L value, then great, then just return param. Notice return param does nothing to it. No operation is performed. But if it turns out it's not an L value reference, that's the way of encoding that it actually was an R value that was originally passed in. And under those conditions, notice that we then apply move to param. And we understand that what move does is simply cast it to be an R value. So we are going to either cast to an R value or not, depending on this encoding of whether the original argument that was passed in was an L value or an R value. Regardless of whether you follow all the details, regardless of whether the pseudocode or any of the details on the screen make sense, what should make sense is standard forward is nothing more than a conditional cast to an R value. Sometimes it casts to R value, sometimes it does not. That's the only thing going on inside this function. If you look at the code here, you'll notice the return type. Now, the return type appears to be an R value reference to T. Appearances can deceive. In this case, they do. If it turns out you're dealing with an L value, then that will actually turn into an L value reference to T. And unfortunately, it takes more time than we have here to run through exactly how that transformation takes place. If you are familiar with reference collapsing, you're thinking, well, duh, it's reference collapsing. And if you are not familiar with reference collapsing, you are thinking, what's reference collapsing? The answer is, you don't need to know. You don't need to know what reference collapsing is to understand what forward does. You do need to know what reference collapsing is to implement forward and understand how it works. But you don't need to know anything about reference collapsing to understand that forward is simply a conditional cast to an R value if the original argument that was passed in as the template argument itself was an R value. It simply recovers R value-ness that was present at the original call site. Real implementations of forward, by the way, number one, they're more sophisticated. Number two, they're a whole lot faster than the code that I'm showing here. And number three, they will compile. This one would not compile. So, but conceptually, it gets the idea across. At least I hope that it does. So the guideline is to understand standard move and standard forward. Any questions about that? Yeah?
Is the deduced type always a non-reference?
Okay, so the question is the deduced type always a non-reference?
Is T non-reference?
So the question is the deduced type always a non-reference? The way the encoding works is that for L values, the deduced type is an L value reference. And for R values, it's a non-reference. I'm not kidding. So it's very simple. L values become L value references. R values become nothing. They just become a non-reference. Okay? So one more question, and we'll go to the next guideline. Yeah?
Can you go to the back to the previous slide, please?
Mm-hmm.
Yeah, as I see, param is T and percent, so it's T. Param is R value.
Okay, keep going.
Yeah, and it's R value, but why do we need to check it for if it's elevated?
All right, so the question is, in the declaration here, what we have is param. It's declared of type T ref ref. And the comment is, this is an R value. So let me lie to you for a moment, because the lie is vastly better than the truth. Here's the lie. It's not an R value reference. It is what I call a universal reference, which means it is a reference which can become either an R value reference if it's bound to an R value, or an L value reference if it's bound to an L value. This is why basically, very briefly, if you are in a template, as we are here, and the type declaration is trefref, exactly trefref, nothing else, then it is a universal reference, my term. And universal reference means maybe it's an R-value reference, maybe it's an L-value reference, it depends on what's passed in. And then I can refer you to information to get more about that. It's a much longer story behind it. But if you read a template declaration such as this as taking an R-value reference, you are going to be misled into thinking it can only bind to R values. All right? Technically, purely technically, it is an R-value reference which, combined with the encoding information on what was deduced, combined with reference collapsing, magically ends up with a giant crater out of which emerges an L-value reference. But I find it vastly easier to understand by saying, don't read that as an R-value reference, read that as a universal reference. I think it will make your life easier. That's a different item in the book, which you could pre-order if I only would write the darn thing. Okay, new topic. In C++ 98, maybe you'd use exception specifications, but probably you would not use exception specifications. They were complicated and the rules were weird and sometimes things slowed down and there were runtime checks and it was messy. So in C++ 11, I am going to encourage you to use no except whenever you possibly can. This is a different piece of advice. So no except in C++ 11 is basically the new empty exception specification. So if I have some func and in C++ 98 I wanted to say that it didn't throw anything, then I would say throw open paren close paren, as I've shown on the second line here. But in C++ 11 we have a whole new fancy syntax for this. We say no except. At a high level of abstraction, they mean the same thing. Unfortunately, we can't sit back with a high level of abstraction because the semantics are similar, but they're not identical. So in particular, they don't behave the same way when an exception gets thrown. So if I have this some func here and I say, okay, it's got an empty exception specification. This is the C++ 98 exception specification, and then somehow an exception actually gets thrown. If an exception gets thrown at runtime, what must happen is first you unwind the stack to the caller of some func. So at runtime, you've got to unwind the stack, and then you're going to end up calling unexpected, and unexpected by default will end up calling terminate. On the other hand, if instead of using an empty exception specification, you use no except, so use the fancy new C++ 11 way of saying essentially the same thing, the semantics are only very slightly different. It doesn't seem very different at all. Under these conditions, what happens at runtime if an exception gets thrown is you only possibly unwind the stack. Now, technically it's implementation defined, so your implementation has to tell you whether they're going to or not going to. And then you call terminate or its replacement. The difference between the two doesn't sound like very much. It's either, in C++ 98, you would definitely unwind the stack. In C++ 11, maybe you unwind the stack, which for most programmers is not a giant difference. But if you are someone who writes compilers, it is a giant difference. It gives you all kinds of interesting optimization opportunities that you otherwise would not have. Now, I usually talk a little bit about the optimization opportunities that arise, but I'm not going to do that here because if you want to know about the optimization opportunities, you are not ever going to find a better place than this conference to ask the people writing the compilers about exactly what kinds of things they can do. So I'm just going to leave things at a higher level and say, if you say no except, that offers compiler writers more optimization opportunities to generate better code. Whereas if you have an empty throw specification, which conceptually means the same thing, there are fewer optimization opportunities. And in fact, you can push this a little bit further. You can also say, all right, so if I say no except, then there's more optimization opportunities. If I say throw with an empty specification, there are fewer optimization opportunities. And if I don't have an exception specification on at all, then there are fewer optimization opportunities still. So I'm encouraging you to use no except when it makes sense, and we'll talk more about that, simply because it allows compilers to generate better code. which was not something we could really say with empty exception specifications. So although there's a very slight difference in the specification in terms of the behavior if an exception gets thrown, it makes a difference to compiler writers. So whenever no except applies, you definitely should use it. This is especially important for move functions. Now, I just talked about how move doesn't really move anything. And what I also find is that people often say, well, you know, move is faster because blah, blah, blah. And that's great if you can do the move. So we've got a move constructor, we've got a move assignment operator, which move-enabled classes will offer to you. And in some cases, you will have code in C++98 which used to do copies. You recompile with a C++11 compiler and a C++11 compliant library, and magically some of those copies turn into moves. Yay, move! Copy, ooh, ick, slow, move, slick, fast, cool. As long as it has the proper behavior. Under some conditions, people would write code in C++98 where they would perform operations that had the strong exception safety guarantee, which meant if an exception gets thrown, then we roll the entire operation back. It's as if nothing happened. This is the strong exception safety guarantee, transactional semantics. And there are a number of functions that you probably use that offer this guarantee. On vector alone, for example, if you call reserve, or you call resize, or you call pushback, you get the strong exception safety guarantee. So consider for a moment pushback. It'd be really nice to know that if I call pushback and an exception gets thrown, that the vector is not modified in any way. If we don't get the strong guarantee, all we'd know is the vector is still in a valid state, but we wouldn't know what was in it. So it's really nice to know if I call pushback and pushback responds with an exception, the vector has not been changed. And in C++98, you get the strong exception safety guarantee when you call pushback. In C++11, pushback can be called with an R value, in which case it does a move rather than a copy. What I want you to think about, though, is let's suppose you do a pushback on a vector and the vector is already at full capacity. So the upper line here, what I'm showing is a vector that is completely full. So I now do a pushback. Oops, not enough room. So what do? You allocate more memory, and now what you need to do is get the elements from the old chunk of memory into the new chunk of memory. So in C++98, which had no idea what moving was, what do? You copy them one by one. Copy, copy, copy. If one of those copy constructions throws an exception, you don't care. The original vector's memory has not been changed. That's why calling pushback can give you the strong exception safety guarantee. Now let's suppose that you're using C++11. Well, C++11 is hip, it's cool, it moves. So you got the same thing. You've got a full vector. You add a new element to it. You call pushback. Inside pushback, no additional capacity. What do? You allocate more memory, and now you start moving elements from one chunk of memory to the other. That's the second set of bars there. And I've put them in a little bit different color to show that after they've been moved, they're not in the same state they were originally. So I'm now halfway through moving these elements from the old memory to the new memory. Oops, the move constructor throws an exception. The original vector at this point has been changed. And there's no guarantee you can go back, because trying to move back, that might throw an exception too. Which means if you're moving like this, you can't offer the strong exception safety guarantee. You can only offer the basic guarantee. That's an interface change. It is possible that clients have depended on the existence of the strong exception safety guarantee when they called pushback. So if you have C++98 code that's dependent on that, if you were to implement things this way, yes, it would run faster, but it would not offer the same interface. That could break client code in the worst possible way, which is silently, by something subtle like an exception safety guarantee. As a result, inside pushback and some other functions, they can't just blindly move things. They can only move things if those things are known not to throw exceptions, which means they don't call move. They call a related casting function called move if no except. Move if no except, also in the standard library, though less well known than move, conceptually, for purposes of this slide, you can think of as saying, cast this thing to an R value only if its move operation is known to not throw. Now, what I want to do is talk a little bit about the difference in performance this can make. Plus, this will give us a little bit of interesting insight into, sorry Herb, one C++, at least as it stands right now. Okay, so I have a constant string. It's called string value, and if I've counted correctly, it has 29 characters in it. I have a class called widget. Widget simply constructs a single data member, a string, with string value. So a widget object consists of a single string with 29 characters inside. That's what a widget is. And now what I want to do is create an empty vector of widgets. And then what I'm going to do is I'm going to iteratively do pushbacks of a widget into this container. Now, vectors grow geometrically, but at a certain period of time, it's going to have not enough capacity. It's going to have to reallocate some memory, and then it's going to have to move things or copy things, as the case may be. And the question is, how long does this take under certain kinds of conditions? So I did some timing earlier this week with a couple of different compilers. So the bars on the bottom, the really long bars, those are Visual C++ 12. And the short bars on the top, those are for GCC 4.8.1. I have two observations. Observation number one, you should not conclude from this that GCC is vastly faster than Visual C++. The reason you should not conclude that is because GCC takes a little shortcut. They don't implement the standard properly. It turns out you can get very substantial performance improvements by not doing the right thing. So you can't compare the two. GCC's strings as of 4.8.1 is still doing copy on write, which is illegal in C++ 11. So that's why those bars are so much shorter. So you can't compare GCC and Visual C++ because it's just not fair. They're doing different things. What I want you to notice is, let's start at the bottom and work our way up. So the long bar that says copy, that's for VC12. That's how long it takes if I have that loop that I just showed you for 10,000 elements. So it takes a certain amount of time. If I then do a moves, now the next two bars are moves. There's move with a empty exception specification, and then there's move without an empty exception specification. The reason I'm not using no except is because Microsoft's compiler doesn't support that yet. But they do support the empty exception specification, which conveys essentially the same information. Yeah, Stefan?
But not with the standard semantics of calling no except. We do something non-standard.
Okay, so this way here, right?
Yeah.
In other words, with the empty exception specification. Yeah, okay.
It's non-standard effects.
Okay. So Stefan simply wanted me to communicate to you that in addition to Microsoft not supporting no except, the empty exception specification is also implemented in a non-standard way. So thank you for sharing that information. If you were a little concerned that I was taking it too easy on Microsoft and picking on GCC, just wait, because we both know where this is going. He reviewed my slides. He literally knows where this is going. What I want you to notice is that the two bars for move with Microsoft's compiler show that they're about the same speed, which means that the exception specification doesn't make any difference in performance. And they're both faster than copying. Now, this is contrary to what I said. What I told you was, if the move operation doesn't have an exception specification, then we shouldn't be able to do a move. We should have to do a copy instead. Now, that's because Microsoft's library is also not implemented properly. So, GCC uses an invalid string implementation, but Microsoft uses a different invalid string implementation. So it's one big fat, happy family we've got here. Now, just a second. In fairness, in fairness, Herb said modulo bugs. These are bugs. These are not grand, major things. But I want to point out something else, and I'll get to you in a moment, Stefan. So if we look at the top three bars instead, if we go to GCC, notice that the copy bar is about the same length as move without no except. Which means if I have a move function that's not declared no except, it takes the same amount of time as copying, which is exactly what it should do. It's because internally inside pushback's implementation, it's not moving, even though you've got a move operation. However, if you add the no except specifier to that move operation, notice the bar gets shorter, which tells you now it is moving and there is a performance gain. if we combine these two graphs, what we would expect is that ultimately we're going to end up with a situation where the bar profile is like GCC. Copy and move without no accept should take about the same amount of time because they should do the same work. Move with no accept should be faster. But the length of the bars probably should be longer, more like Microsoft's implementation, because GCC is cheating and they're not doing what they're supposed to be doing. So, nevertheless, what's interesting is that we can see that moving does make a substantial difference. And remember, in this silly little benchmark that I'm showing here, number one, we're only dealing with a vector of 10,000 elements, which really is not very many. But at the two smaller versions of the same bar graph, the one on the lower left is for 1,000 elements, and the one on the lower right is only for 100 elements. The same profile exists there. So moves make a difference, even if the only thing you're dealing with is a 29-character string. So, and Stefan, did you want to chip in one more thing?
Yeah, the Microsoft bug here with the move with throw not being smaller, that is actually a bug in vector. String, in that case, is blameless.
Thank you. Okay, so I'm sorry. I completely misplaced where their bug in the library is located.
We feel super bad about it.
Okay, he said they don't feel bad about it. They feel super bad about it. So, okay. Yeah, one more comment, then we do have to move on. Yeah, Chandler.
Have you tried LVM?
Okay. So the question is, have I tried LLVM? And the answer is no. Have you made a binary downloadable for Windows yet? Would you like some water? Okay, so, but let's move on. Now, I want to talk a little bit about standard move if no accept, because standard move if no accept, I mean, this is the key thing that's being used deep down in the library internals. Standard move if no accept. So this is the definition of standard move if no accept. I actually copied this out of the standard. I think it's fairly clear, speaks for itself. Doesn't really require any elaboration. But I'm a speaker, ergo I must speak. So what this thing is actually telling you, notice the returns, which I literally copied out of the standard. All it says is it returns move of x. So all it's doing is an unconditional cast. What it's doing is it's playing games with the return type, which will actually, under some conditions, undo the results of the unconditional cast. Therefore, making the unconditional cast a conditional cast. So, you think I'm making this stuff up, don't you? Alrighty, so let me translate the stuff in red, because the stuff in red is the condition that really makes a difference. The translation is, we're going to cast this thing to an R value. It actually is going to perform the move if T's move constructor doesn't throw, which is what we expect, or it's not copy constructible. Otherwise, we're not going to do anything at all. Now, what's sort of interesting about this is that if you have a move-only type, for example, a unique pointer or a thread, things that can't be copied but which can only be moved, under those conditions, because they have no copy operations, then you will get a move even if the moves throw exceptions. So move if no accept doesn't really mean move it only if it doesn't throw an exception. It means move it if moving won't throw an exception or if there's no other choice. And this is not a problem for legacy code, because in legacy types there was no such thing as a move-only type. So if you have a move-only type, by definition, you're not trying to preserve the semantics of C++ 98 code. So there's nothing actually wrong with what's going on inside move if no accept. You just need to bear in mind that under some conditions it will move even if that might throw an exception, but that's okay because we're not breaking legacy code. So it actually is put together pretty nicely, but it's still worth knowing how the pieces fit together. Which leads to this critical question. Okay, if it's so important that I communicate to my compiler that my type has a no-throw move operation, how do I communicate that to my compiler? Now, remember, the standard library, it's going to be calling move if no accept. So I go back a slide, and what move if no accept is going to do, it is implemented this way. What it's going to do is it's going to consult, is no-throw move constructible? Which means it becomes really important to find a way to communicate to the library through is no-throw move constructible, whether my type throws. And the way you do that is to tell your compiler. And the way you tell your compiler is to declare your function no except if your compiler will let you, or to use an empty exception specification. Both of those should convey the information which the compiler then has to actually pipe through the library ultimately to get to the library implementation. So my understanding currently as to what's going on in the Microsoft compiler, for what it's worth, is that the compiler is correctly picking up the information that this type is no-throw constructible. So the compiler is doing its job. It is then feeding that information into the type trait that says it's no-throw constructible, which is then promptly not being consulted by vector's implementation. So it's actually a library problem, not a compiler problem. So, but they feel super bad about it. Now, my advice here is to declare functions no except whenever that's possible. It's very important to recognize the whenever possible part. No except is part of a function's interface. So clients who call your function are going to become dependent on it, for example, for exception safety guarantees that they offer. If you were to change a no except function to a non-no except function, that could break client code. That's an interface change. As a result, if you have an implementation of a function which currently doesn't throw exceptions, that doesn't mean you should declare that function no except, because it's an interface promise you are going to be making. So the decision as to whether to declare something no except or not declare it no except is based on interface considerations alone. It is not based on the implementation. As a general rule, if you're not sure that you want to commit to never being able to have an implementation which might throw an exception, you wish to not use no except on your functions. So my advice here is not use no except everywhere. That's not my advice. My advice is use it whenever it's possible. And it's possible if you have determined that the interface to the function should offer that guarantee. Under those conditions, don't just document it in comments, actually put it in the code. That's what permits compilers to generate better code. That's also, for example, what will allow library implementations like pushback when they consult your types to find out whether they can really do a move or whether they have to do a copy due to exception safety guarantees. There are the decision whether to say that a function is no except has interface implications and also has implementation considerations for other code that will be ultimately using your types. Most code is exception neutral, which means that if an exception occurs higher on the call stack, it can go streaking right through the stack frame, keep on going, get caught by somebody else, and your code will simply maintain all of its invariants. Under those conditions, you can't say you're no except because an exception might go propagating through you from somebody else. Most code is exception neutral. That kind of code is not going to use an exception specification of any kind. This is what most of your functions are going to look like. So I'm not telling you run around looking for opportunities to put in no except in places where it doesn't belong. What I am saying is that if you have determined that you want to make the interface guarantee that it's not going to throw exceptions, that's the place to use no except. But most functions, being exception neutral, like this function, common function, is not going to have an exception specification. We've already seen that the move functions should be declared no except whenever possible. So you might expect that if you crack open the standard library, you're going to find lots and lots of no except move functions. And perhaps that is true, but I can tell you that if you go and you look at the containers, for example, which are fairly heavily used things, the containers, none of them have no except move operations. So, for example, I copied this out of the C++11 standard. So here's list. You can see that list there's the move operator for list. Notice it is not declared no except. The same thing is true of every one of the containers. Now, okay, the same is true for every one of the containers, which is rigorously true, I hope, because now I see Stefan raising his hand. Yeah, Stefan.
It's not the allocators that are to blame. Allocators are actually required to be no-throw, copy, and movable. In this case, it's either debugging allocations, or in the case of list, list can have a dynamically allocated sentinel node. BC has one, GCC does not. And move construction needs one of those. So that's where the throwing potentially comes from, in addition to like debug allocations.
Okay.
Once, allocators are not to blame.
Okay. Okay. Stefan said, Scott, you are so ignorant. I'm paraphrasing. So the last line, what I said was, in general, moving their allocators may throw. Stefan points out that that's not actually the reason, followed by blah, 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 which I didn't really follow the details of. But I'm sure is completely accurate. The higher level point is that if you look at the standard library, you're going to see that they don't always declare their move operations no-throw. So this doesn't mean blindly declare your move operations no-throw. It means declare them no-throw if you can. And if you can't, then you're going to end up with things like pushback, falling back on copy semantics, but it will still maintain the strong exception safety guarantee, which is considered more important. Remember, making things fast and wrong is generally easy. So correctness is something we value more highly than that. Thank you for the correction, Stefan. So whenever no except is the appropriate thing to do, then you definitely want to use that. If you declare a move, if you declare your move operations, and if they can be declared no except, then what you also should do is encourage clients who have been copying your objects to review their use cases. Because in the past, if you had a possibly throwing copy operation, copy constructor, for example, or copy assignment operator, if it might have thrown, and now you have now you have augmented the class with move operations, which you can legitimately declare no except. That means that for clients who are performing what look like copy operations on R values, now they know it can't throw an exception. And that may permit them to offer stronger exception safety guarantees under certain conditions. So essentially, if you have some copy operations and they might throw, you add move operations that can't, clients now might want to go back and review the exception safety guarantees that they are offering. Most people know about no except. In my experience, fewer people know that no except actually takes a compile time Boolean expression. So if I say that f is a function which is no except, that's a shorthand for no except true. And if I have a function which doesn't have a exception specification on it, that is a shorthand for no except false. And in a language that likes negation, no except false means that the function is not guaranteed not to throw. That's what it means, no except false. It's not guaranteed not to throw. Doesn't guarantee it will throw, just says it doesn't guarantee that it won't throw. No except is also an operator. You don't have to just put true and false, though. You can actually put in Boolean expressions, and no except itself returns a Boolean value. And as a result, it becomes possible to declare functions conditionally no except. This is common for templates, where a template might need to say, I can offer the following no except guarantee if all the operations that I perform on whatever type T is passed in offer that particular exception safety guarantee. Exception guarantee. So in this case here, I've got a function called f, and what it says is it takes some parameter, and I will remind everyone in the room that trefref is not an R value reference. It is a universal reference. It accepts both L values and R values. And in this case, what this declaration says is if I take param and I dereference it, whatever that means, applying the star operator, if that operation is guaranteed not to throw an exception, so if it's no except, then this template also is no except. But if the expression star param potentially could throw an exception, which means it's not no except, then this also is not no except. So this is a way of formally implementing conditional guarantees for exceptions for exception safety. This turns out to be really important, for example, for swap in the standard library. If you take a stroll through the standard library specification, looking at various swap functions, what you're going to find is that a lot of swaps are conditionally no except. So this happens to be swap for two arrays. And what this says is swap for two arrays is no except if swapping their individual elements is no except. And this is for pair. And this says that swap for pairs is no except if it is guaranteed that you won't throw an exception when you swap their first component, and you won't throw an exception if you swap their second component. Also conditionally no except. And this is swap for a queue. If you got two queues, and if I have two queues, then basically it says if they're individual. So this is the non-member swap for two queues. And what it says is it's no except if the member swap for the queues is no except. So you'll see that there's a lot of conditional no acceptedness for various swap functions. This is important because whether swapped is no except often depends on other swaps, as we've just seen, and whether the callers of swap can be no except depends on whether swap is. And the optimization of the swap function itself, as well as the callers of swap, are dependent on their no except status. And as a result, and also with the observation that swap itself is very frequently used, especially in things like algorithms, copy assignment, stuff like that. Swap is a function that if you can declare it no except, number one, it can be implemented, it can have better code generated for it in the more general case, but also it tends to propagate across lots of other use scenarios in your code. So if you can declare swap no except, you definitely should. Now, this is simply a noteworthy case of the general rule, because my general rule is that you should declare functions no except whenever possible. I focus on swap because it's an important special case. And I talked about the move functions, which are also an important special case, because I can show secondary implications, for example, what's going on inside the standard library. But I want to emphasize that first point I made, which is that compilers in general can often generate better code for functions if they know that no exception will come out of them, is true for every function. And that's why the guideline is to declare functions no except whenever possible. Yeah?
I just tested GCC 4.7 fixed that problem.
Fix which problem?
It only moves when it's supposed to now. In vector, remember you showed the vector
No,
repeating?
VC had that bug. GCC's bug is it still uses copy and write strings. You got multiple compiler bugs here.
I obviously have another one here too.
So, okay, I'm going to twist what you said around, but it's actually going to be accurate for both of us. Okay. So here's the accurate for both of us version. He just did some testing with GCC, and what he found was that they do correctly look at the no except specifier when generating code. So it's essentially a confirmation of what I already claimed. So thank you very much for doing the testing. Did you try Clang?
Do you have a binary for Ubuntu? Oh, wait, you do.
Chandler, did you try Clang?
I don't have your code yet.
Fair enough. All right, any other questions about no except? Oh, yeah, go ahead.
It might be useful to note that although standard library moves are sometimes potentially throwing, standard library swaps virtually all never throw, and they're guaranteed so by the standard. Stood array is the exception.
Okay, so Stefan's comment is that although move operations in the standard library may not be declared no except, such as in the examples I gave with containers, the swap operations are virtually guaranteed to never throw, and there's one exception, which is standard array. Is that correct?
It's the only one I can think of.
Okay, so there may be some other ones, but basically, so essentially swaps almost never throw in the standard library, but the move operations may or may not throw, depending. Yeah.
Because of that, wouldn't it make sense to have a switch if in the standard library you say vector, if the type can't be moved no throw, then do this, and it can be swapped no throw, use the swap. That way you can still keep your no throw semantics.
It doesn't buy anything because during reallocation, we need a fresh memory block. So if we try to swap, we'd at least need a default construct. And whenever your move throws, your default constructor is basically going to throw. Life is hard.
So the question was blah, 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 and the answer was blah, blah, blah. So the end result was nothing changes. So, and for those of you in TV land, this is why you tune in. So, yeah.
Just a side note, lab C++ is implementing a way beyond the standard. It behaves correctly, even the allocator can throw, move, or copy, or construct.
Okay, and which implementation is that?
Lab C++.
Okay, in libc++? Okay, so libc++ is addressing these issues and goes beyond what the standard says. Is that what you said?
Yeah.
Okay, great. So, unsurprisingly, unsurprisingly, number one, Herb's comments were accurate. And also, unsurprisingly, we are going to get convergence among library implementations. I mean, if you think about it, if what we have to worry about in terms of one C++ and convergence is whether or not deep down in the bowels of the library, things are being properly implemented about exception, checking for no except status on move operations, we're really within a tiny delta of getting full conformance. So we're in good shape. I think it's worth knowing about, but I would not consider this a big deal. A big enough deal to be worth talking about, but not a big deal. So, all right, last thing I want to talk about, last guideline, is to make standard threads unjoinable on all paths. A standard thread object can be joinable, which essentially means that the standard thread object, if it's joinable, essentially represents some underlying thread of execution on the operating system. That's essentially what it means. There's some thread of execution that corresponds to that thread. An unjoinable thread does not correspond to any thread of execution. And there's a variety of ways you can get an unjoinable thread. For example, if you default construct a thread object, it's not running anything, it's not doing anything, there's no underlying thread, that is an unjoinable thread. Excuse me, that's a, that is an unjoinable thread. If you have a thread, you started doing some work, and then, for example, you do a detach. When you detach the thread, it no longer corresponds to an underlying thread of execution. If you have a thread object and it does correspond to a thread of execution, and you move it to another thread object, then the thread object you moved it to becomes responsible for that thread of execution, and the original thread is now unjoinable. It's no longer responsible for that thread of execution. Or if you have spawned off a thread and then you join with it, now your thread is unjoinable. There's no other asynchronously running thread of execution going on at this point. So there's a variety of ways you can get unjoinable threads. If, however, you have a joinable thread and its destructor gets called, you call terminate. Your program stops. So in this example here, I open a block, I create a thread job T, I'm running some function, and then I execute my favorite code, which is ... Always works perfectly for me. I'm going to assume that inside that ... the thread remains joinable. So I don't do a detach, I don't do a join, I don't move it to any place else. And then at the end of that scope, the local object T goes away. That means its destructor gets called. Under those conditions, terminate gets called. I am going to proceed on the assumption for the remainder of this presentation that you would not like your program to end in this fashion. Probably not what you're shooting for. And I will also remark in passing, this is different from the way Boost used to behave. Prior to Boost 1.5, what Boost threads would do is they would do an implicit detach. But the standardization committee decided that they don't like implicit detach. They had some legitimate technical reasons for doing that, so they specified things differently. And since Boost 1.5 and later, Boost now follows this same behavior. So Boost will also terminate. Now, so my guidance here is that your thread should become unjoinable on all paths from a block. So there's two key things here. Number one is unjoinable. So what does it mean to become unjoinable? So you've either got to join, or you got to detach, or otherwise be made unjoinable. For example, typically being moved from would be a way to do that. But the key thing really is all paths. On all paths through the block. So that has to take into account continues, breaks, gotos, which are still legal in this language, returns, flowing off the end, which occasionally we do, especially if it's not a function block, but it's just inside a block. All paths. If there's an exception, you've got to make sure that all these things get taken care of. You have to make sure that your thread becomes unjoinable on every single path. Now, Anytime we're in C++ and somebody says this has to happen on every path out of the block, you should instantly think, clearly we need an RAI class. That's obviously what these things are made for. So we clearly need this kind of a class. It is the standard library to the rescue, whereby it offers the following information. The information is, we got nothing. And they even point out why they got nothing. So what they say is, if you implicitly detach, that leads to problems. If you implicitly join, that leads to problems. As a result, we're just going to kill the program. All right, that's legitimate. But it doesn't change the fact that we still are stuck with a situation where we are now responsible as developers for making sure that if we have a thread object, every single path out of a scope, we have to make sure it becomes unjoinable. So fortunately, it's not that hard to write your own. So this is one that I threw together. This is just an RAI class, and all I'm going to do is I'm going to set it up so in the constructor I pass in the thread object and whether to join or whether to detach at destruction. That's all I'm going to do. So I've got a constructor here, and the constructor takes the thread object, takes it. That actually is an R value reference. The ampersand there really is an R value reference. Threads are only movable; you can't copy them. And then it takes an RAII action, and you can see in the type def that the RAII action is simply a pointer to a thread member function. And I'm thinking you're going to pass in either join or detach. And then what I do in the constructor, unsurprisingly, because it's an RAII class, I simply move the thread into a data member, and I then also store the pointer to the member function I want to call upon destruction. Then in the destruction, what I do is, first I make sure that it's joinable, which is a member function on thread, so you can query to find out whether it's joinable. This is important because it's possible it became unjoinable in some other way, and it is it's either undefined or throws an exception, or something bad happens if you invoke one of those member functions on an unjoinable thread. I don't remember. Anyway, so what I do is, assuming it's still joinable in the destructor, I then invoke whatever action was passed in. And user code would look like this. So if I want to make sure that I'm going to do a join on this thread object, regardless of how I leave the scope, then I can say, okay, T1 is going to do, it's going to do this work asynchronously on a thread. And if in its destructor we haven't joined yet, we're going to do a join, so it'll basically block. And otherwise, what a client might decide to do, just a moment, what a client might decide to do is they might decide to run something on a thread, and then they say at the end, I want to do a detach. So, did you have a question?
If thread already are reference, why do you need additional move?
Okay, so the question in this case is, I've passed in the thread object as a parameter, as an R value reference, which means that we know we're bound to an R value. And so the question is, why do I have to do a move on it afterwards? It's because anything that has a name, like that parameter thread, is by definition an L value. The best approximation of whether something is an L value is whether you can take its address. So that parameter thread, you can take its address. As a result, it is an L value. So even though we know it's bound to an object which is an R value, that parameter itself is an L value. And as a result, we have to turn it back into an R value in order to move it into the local data member. Say that to yourself about 100 times. You are halfway there. So, was there another question over here, or?
Maybe I'm missing something. Join or detach should not be called on a unjoinable thread. Is it correct?
Okay.
And now there is no synchronization in the destructor. We ask if the thread is joinable, and now it becomes unjoinable, and we call the action. How is that?
Okay, so the question essentially has to do with what's going on inside the destructor. So what we're going to do here is, what we say, so we're destroying the thread RAII object, so we're leaving a scope. So what we do is, first we make sure that the thread is joinable. Because if it's joinable and its destructor gets called, then it's going to call terminate. So we have to make, so if it's joinable, that means in some sense it's still running. You can think of it as it's still running. So then what we do is we call, let's say, join.
Can it become unjoinable asynchronously?
may no longer be joinable.
I believe actually that the code is correct.
There is a potential race condition.
The question is,
Wait.
Wait, let's.
I have the answer.
Okay.
I don't know.
Okay.
Sometimes that's the answer. No. So here's the issue that's being raised. Let's suppose we check for joinability, and then we find out that it's joinable, and then before we get a chance to invoke the action, it becomes unjoinable. Then it sounds like we can have a race condition where I check to find out whether something would be valid, and then when I go to do the thing, it's no longer valid, and therefore I have a race condition. I don't remember offhand what the standard library says about this, so I will find out. So if anybody in this room or anybody watching this, either now or later, wants to find out what I find out, feel free to send me email, and I will find out the answer, and I will tell you what I find out. I take some minor solace in the fact that I heard Stefan saying, no, that's okay, which means that with 99.9% probability, it's okay. But I will find out. It's an excellent question, and I'm sorry I don't know the answer offhand. So. What's that? Okay, so the comment is Boost has a scoped RAI wrapper, but we'd have to look inside. Anyway, I don't know the answer, so I'm not going to make it up as I go. I see. Okay, so the comment is that if you don't want to write your own and you want to take advantage of one that has been through Boost's review process and is used by people, then you could go to Boost, which is an excellent suggestion. Thank you very much. Alrighty. So another thing you can do is you can say, all right, threads are pesky anyway, and they've got a bunch of other problems that I haven't talked about as regards using threads directly. Maybe what I want to do is turn over that whole thread management nonsense to the runtime system and use a higher level abstraction like async. Now, if I call async, it's going to give me back a future, in which case I don't have to worry about the lifetime of the thread or any of that kind of nonsense, none of this terminate stuff. The nice thing about async is it doesn't have this problem of destruction leading to calls to terminate. It has different quirky behavior. In particular, the exact details are that the future that you get back from async refers to something known as the shared state, which is where the result is actually going to go. And if you end up with a future that refers to a shared state that originally was created due to a call to async, and you are the last future referring to it, then in your destructor, you will do an implicit join. Now, what's interesting about this is async, what I just said boils down to, if you call async blah, 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 do an implicit join. Wait, what does the standard say? It says that doing an implicit join leads to problems. Now, it turns out that if you have a future and it refers to a shared state that originally was created in a call to async, but it's not the last future, then you just flow through your destructor and do nothing, which is almost the equivalent of doing a detach. So as I like to say, when the standardization committee was faced with the difficult problem of figuring out what you should do if you have a handle to some asynchronously running thread, they couldn't decide whether the right thing to do was an implicit join, an implicit detach, or terminate, so they chose all three. And the behavior of futures that come back from async has been proposed for a change in C++ 14. Herb is one of the people who has authored that proposal. I'm not going to try to say what is likely to happen. What I will say is that the committee is certainly aware of this different kind of behavior about what happens when threads go away and you have a handle to them, where by handle I mean either a thread object or a future, and they're considering changing what the specification is. For the time being, as developers, what you need to remember is that if you actually do create thread objects, you definitely want to make sure that you make it unjoinable on all paths out of your scopes. So the guideline is to make threads unjoinable on all paths. And to summarize the 3 guidelines I talked about today, the first one is to understand move and forward. Move, unconditional cast to R value. Forward, conditional cast to R value. Secondly, to declare functions no except whenever possible. This is primarily for improving performance, but only put no except on functions where you're willing to make the interface promise that is never going to throw an exception. So this should not be something you do for performance tuning. It's the kind of thing where if you can make that guarantee, then you want to make it because you get better performance. And finally, we talked about making threads unjoinable on all paths. And we're out of time, so it's lunchtime now. I do not want to go into lunchtime. If you have any questions, I'll be hanging around for that. When I make the slides downloadable shortly, there's also a list of recommended readings so you can follow up on these topics if you want to. Thank you very much.
Thank you, Scott.